pleasure to be back in San Diego, where much of the early days of this story were told. So my talk is in three parts. I'm going to tell you what metamaterials are, and then I'm going to say why they might be useful, and then very briefly I'm going to indicate what the future might be. So if you want to do something with light, if you want to make a device that controls light, you have to make it out of something. And it turns out that in optics, and in fact in electromagnetism generally, the material you may wish to have is not there. And that's where metamaterials come to the rescue, because they have properties which are not found in nature. So the first part is, what are metamaterials? So you know what a conventional material is. It comprises atoms, molecules, and the way the material responds to light is dictated by the atomic composition. And the requirement is that the radiation is has a wavelength which is much larger than the atomic structure. It doesn't quite work for X-rays. You can't describe crystals in the way you describe them for light, because what light does, because its wavelength is much greater than the size of an atom, it takes an average over many, many atoms, and so you see that average. If you want to change the properties, traditionally you change the chemistry. So in the case of glass, you might add some lead to the glass, and that will make it more refracting, more sparkling, to make wine glasses out of it, and so on and so forth. But there's another way in which you can change the properties of a material, and that is to make some structure. Now, an atom is about a nanometer across, less than a nanometer. A molecule might be a nanometer or a few nanometers. Wavelength of light is a micron, 1,000 times bigger. So there's a lot of space there to have a structure which satisfies this requirement that it's much smaller than the wavelength, and still performs the same function as an atom. And if we sort of say, well, okay, we don't have to be as small as a nanometer, maybe 10 or 100 nanometers might be possible, and then that's the sort of structure we can engineer. And in fact, if we go to much longer wavelengths that are involved in radar, then the structures need only be a few millimeters across, and they're dead easy to make. So that's the way things work. It's making physical structures that change the properties of the material. So just to continue that story, the atoms respond to light. Each atom will respond to light in a way that's dictated by transitions between the atomic levels. And if we look at the response of an atom, say, to an electric field, the polarization or the dipole moment of the atom, as a function of frequency, then if the frequency is much lower than the transition frequency of the atom polarizes, the electrons move in the same way the electric field pushes them. Now, it may seem strange, but if you try to push the electrons too fast, and by too fast I mean at a rate greater than the frequency of the transition, then the response is negative, and that will be important part of the metamaterial story. And you can understand this by thinking of the simplest possible resonance, which is a pendulum. So if you suspend a weight and just let it go, it will swing with a natural frequency. That's the resonant frequency. And if you want to set the pendulum in motion, you can move the support, and if you do it slowly, the pendulum will follow where you push. But if you try to move it very quickly back and forwards, you'll get a motion like that. Try it, and you'll see the pendulum swings in the opposite direction to where you're trying to push it. And the atom's just the same. If you try to push the atom to polarize, and you do it too quickly, then you get this this negative response here, and that will be part of the story. So the atoms, you put them together and you make a structure like a prism, for example, which can diffract light and send it in a different direction from that which you started with. So let's go straight to metamaterials, and this is one of the earliest structures, a so-called split ring structure, which we devised. And the idea here was, in the first instance, to make magnetism without having magnetic materials. So this is made of copper. Now, if you put a magnetic field down the center of this ring structure, through induction, that field will induce a current which flows round the ring. And, as many of you will know, if you get a current flowing round in a loop, it will generate a magnetic field of its own. So this structure, although there's no iron in it or nickel or anything magnetic, just copper, it will have a magnetic response to radiation. In this case, it was RF radiation. Now, something you notice about this ring, and it's split. So if you want current to flow round the ring, it has to somehow jump across this gap here, and it does so through do that because there's a capacitive conduction across gaps here. So electricity can jump across gaps through capacitance. So what you have here is electrons flowing round in a ring. That's an inductance. And jumping across a gap, which is a capacitance. And as many of you will know, an inductor and a capacitor makes a resonator. So there we have again, not on the atomic scale, but in this case, the scale of this ring as it was originally built is about 1 centimeter across. You have this characteristic resonant structure of a positive response to low frequencies and a negative polarization. In this case, it's a magnetic response, not an electrical response. But there are other structures we built which have electrical responses, and they show this very characteristic curve here, positive, negative. Here's a paper which I wrote following the PEX conference in Laguna Beach in 1998, or was it 99? About that time. The paper was published in 1999. And that was a very significant conference for me because it's when I made the first really public presentation of these ideas we've been having about function through the structure rather than through chemistry. And there was a very positive reaction at the conference, and one important thing that happened there was I met two people who are very important to this story. One of them is here today, and that's David Smith, who's in the front row there. Hello, David. Who was a postdoc at the time in San Diego. And the other person was Shelley Schutz, who was head of the group in which David worked. And they were very excited about this because they knew that this ability to create magnetism in a very novel way with positive or negative features was really something interesting. Now, subsequent to that meeting, the story of metamaterials told in publications starts really with the IEEE paper, though we did publish earlier papers in 1999, and something I'll come to in a moment, negative refraction was realized experimentally in the year 2000, and that created a lot of excitement. Actually, the word metamaterials didn't begin in 1999. There's no mention of metamaterials in this paper, and it was subsequent in about 2003 that we began to call them metamaterials. And then there's the realization of a cloak of invisibility, which caused a lot of interest amongst Harry Potter fans and other people. And the subject has continued growing until the publication rate here is about 3,000 or 4,000 papers a year, quite a lot of interest. And the other significant thing about this growth of the field is that it's not just confined to a bunch of physicists and electrical engineers. It has branched out into all sorts of areas. So here is an analysis from the web of the breakdown of the 40-odd thousand publications that we have so far. So physics, yes. Optics, of course. Nanoscience, telecoms, chemistry, mechanics, material science. There's a whole host of areas on which the concept of metamaterials has had an impact. So you saw that common theme of having this structure, this split ring, which is resonant, and its response, although it doesn't in this world look anything like an atom, but nevertheless, electromagnetically speaking, it has many similarities to the atom, and that's why we can use them to make these metamaterials. Here's the first. Well, it's not the first, but one of the earliest realizations by Mike Wiltshire. I was consulting for the Marconi company at that time of fond memory. I was so enthused by the success we had at Marconi that I invested all my consultancy money in Marconi shares. Companies subsequently went bust and they got all their money back. Yes, sad story. Anyway, so those were the first structures by Mike Wiltshire, and those structures were on a scale of, sorry, I should have explained more about this. So this is designed to work at radio RF frequencies of about 10 gigahertz, and that's a wavelength of about 3 centimeters, I think. This structure is a few millimeters across, and actually Mike didn't make the structure, he designed it, and he sent off in the email the design to a printed circuit board company, and they manufactured it using existing technology, and back through the post came this early realization of a split ring metamaterial. And I think that was one of the reasons for the early success, because it was just so easy once you'd announced the concept for people to do just that with all sorts of different structures they could think of, and you soon got an experiment going in your lab. Pretty soon people were doing structures on a much finer scale, so that was a millimetric scale. This is designed to work in the near infrared. It's called the fishnet structure. It's a resonant structure consisting of layers of dielectric and silver, and it's designed to have a negative refractive index. So that's the design, and this is the realization of it, an electron. I think it's an electron micrograph of the structure. And the scale here is 1 micron, so you can see things are getting quite small. So I want to get on to negative refraction. This is the world that Newton was aware of, in which the light enters a material. Here's the normal to the surface, and it's bent towards the normal if you have a higher refractive index there. And there's a law called Snell's law. Many people claim invention of it. Newton quoted the law without acknowledging any source. It's also in France known as Descartes' law. So depending where you live, so you own your version of the law. What is never found in nature is this situation here, which is negative refraction. So the difference between these two is that the refracted light emerges the other side of the normal. So if you count this as a positive angle, this will be the opposite, it will be a negative angle. So according to Snell's law, if one of these angles is negative, then you have a negative refractive index, and as simple as that. Now you might say, what's the significance of a negative number? Negative, positive, we have imaginary numbers. And in the first instance, you might think it's not special at all. But as soon as you start sort of asking questions, what can you do with negative refraction, you come across all sorts of paradoxes, which led to some very heated arguments, actually. And negative refraction is rather special. And it was first investigated seriously by a Russian scientist, Victor Veselago. He was a lovely man, and lived to see his ideas of negative refraction realized through metamaterials. Sadly, he's not with us anymore. But in 1968, Victor wrote a long paper, and in that paper he said, if you want to make something which refracts negatively, this is what you must do. So I've talked about the magnetic response of materials, I've talked about the electrical response, and I've said that they can either be positive or negative. And what Victor said was that if they're both negative at the same time, then you get a transparent material and it's negatively refracting. Now, that caused a huge stir at the time. People were very interested in this paper. It was full of all sorts of interesting predictions. Victor was regaled with a tour of the USA, and many of the great intellects of the time, like Marvin Cohen, were interested in what he'd done. But it's a lesson for us all in that, try as they might, people could not find a natural material in which both these things happen together. They happen separately, but not together. So people sort of went away, and the idea was forgotten for many years. So I like to show this this sector here, this circle divided into 4 quadrants. So this is the electrical response here, positive electrical, negative electrical response, positive magnetic response, negative magnetic response. And when they're both positive, you get something like glass, something which is transparent. If you make epsilon negative, then that's what happens in a metal. And it turns out that just making one of them negative, the thing isn't transparent anymore. So that's also true if you make the magnetic response negative. You can't see through things with a negative magnetic response, but you make them both negative, and you get back into something which is transparent, but different. So here's what we get with a negative refractive index that, as I've explained, you get the light refracted onto the other side of the normal. It would, in ordinary glass, it would come this side, and a negative refractive material comes this way. And what I draw here is the wave vector. Now, there's a bit of technical stuff here. When you have a wave, there are 2 velocities to bear in mind with a wave. Often they're the same. So if you think about a packet of wave, a wave packet as they say, then you have the group velocity, which is the way the packet heads. Now, you might think, and it is true in air and in most materials, that these little waves inside will go along with the packet, but they don't have to. And in fact, in a negative refractive material, they cannot do so. They head in the opposite direction. So you look at this wave going that way, and hey, there's something peculiar about it. the actual waves seem to be going backwards. So they come in, they grow, and then they go out of the back. Very, very strange. And in fact, that follows from a rigorous law of mathematics, which says that if you have a vector here, which is the group velocity, and a vector here, which is the wave velocity, then the group velocity can do more or less what it likes here, and in this case, it's negatively refracting. But the wave vector there's a very, very important restriction on it, and it is that its component parallel to the surface must be the same either side. And so you see, you can't wriggle out of it anyways. The wave vector, the velocity of the waves, has to be opposite to the velocity of the packet in which they're contained. There's no way around that. And it's a very, very, very strange property. Negative refraction, I'll skip over this slide because I'm going to talk about it quite a bit later. So I did mention that at that Laguna Beach meeting, I met David and Shelley, and boy, do they act fast. Very, very soon after the conversation, they made this structure here. Let me show you what it's about. I've talked about these split rings, and perhaps you can recognize that they've been squared away somewhat, but they're still split rings. Something else that you can't see so well. Can you see a little black shadow there? That's a wire which is on the other side of the circuit board. And that gives you the other part of the story. So the split rings give you a negative magnetic response. The wires are resonant, and they give you a negative electrical response. So here is the response of the rings, which we've discussed before. Here's the response of the wires. It looks like an atom. And there's the operating frequency, which comes when they're both negative. Now, neither myself, nor David, nor Shelley knew about negative refraction at that time. And it emerged. Isn't this right, David? It came through the refereeing process that somebody pointed out, hey, there's this guy, Veselago, and you've actually made his stuff. And so the paper was really, that resulted from that structure, really became very famous. And created a great deal of debate. Okay, so that is the first material with negative refraction. But before I take that story further, I want to talk about a technology. So we had these metamaterials which could do many things which were not possible before. And then we had negative refraction. And the prime design tool at that stage, well, you had a choice at that stage how to design devices. One was still used, is Snell's law, hundreds of years old. Its great virtue is that you can actually see in your mind's eye the rays of light going here and there, and that greatly aids your imagination and the design process. The other is but Snell's law knows nothing about reflection at surfaces. It knows nothing about the wave nature of light. And to include those, you have to go to Maxwell's equations, which are exact at the classical level. But they are quite complex. And I challenge you to stare at Maxwell's equations and say, well, this particular thing negatively refracts at the surface. Maybe some very clever people in the audience can do that. I can't. So we wanted something which was exact in the same way that Maxwell's equations are, but which at the same time had that visual aspect to it. And we seized on, instead of manipulating rays, which are an inexact concept, we talked about the fields. Now, you probably know that the electric fields, and particularly the magnetic fields, can be represented by lines of force. Have some of you seen that experiment where you put a piece of paper over a magnet, and then you put some iron filings on the top, and then you trace out those lovely curves? Those are the field lines, and those are the things we're going to work with because of the components of Maxwell's equations, and so we're on to something that might well be exact. So this new vision has this exactness, but also it carries with it the intuition that we get from a picture in our heads, which Snell's law gives to us. And now with this we can do things like design metamaterials, and we can also manipulate things on a scale much smaller than the wavelength of light. If you're smaller than the wavelength of light, you can't think of rays, because a ray has to be fatter than the wavelength, otherwise it doesn't stay as a ray. And people are very interested in nano-optics through plasmonics and so on. And we want a design tool for that as well. And transformation optics will satisfy that requirement. What is it? Well, we go back to Einstein. And before the time of Einstein, people thought of space, they ran out of words for nothing, okay, emptiness. But Einstein said that, oh no, space isn't empty, it's just another material. And it happens to be made of rubber. You can distort rubber, you can pull it, you can push it in different directions. Unfortunately, in the case of space, you need a black hole or something very, very massive to distort and stretch space as if it were rubber. And one of the predictions of Einstein was that you could bend light in this way. So Einstein replaced Newton's laws of action at a distance with nothing in between. Einstein said that there's another way of looking at that. It may sound a bit more complicated, but in fact it's more accurate. And that is that a gravitational mass actually distorts the space around it. And that's the reason that planets move in an orbit, because they're not moving in a flat space. This space is curved, and therefore they follow, in some sense, the curvature. Now, if you take Newton's picture of action at a distance, space has nothing to do with light, other than letting it go through. You don't change space in Newton's picture. So light goes in a straight line, no matter what. But in Einstein's picture, it's not true, because light goes through the same space that the planets are moving through, and it's curved. And so it should bend. And that was a prediction Einstein made in his theory of general relativity. And in 1919, Arthur Stanley Eddington made an observation of the refraction of starlight by the sun. And you can only see a star going behind the sun when the sun is eclipsed. And so there are actually two expeditions, one to South America, one to Africa, which observed. One happened to be on a cloudy day. Eddington's got the sun, and he made a measurement, and that is one of the pillars on which Einstein's laws of general relativity sit. There's a sort of human story there, because 1919 was just after the Great War, in which both their countries had suffered grievously. And Eddington was a pacifist, and he saw this experiment as a confirmation by a British scientist of a German prediction as a way of bringing the two nations together through science. Well, since then, there have been other observations. This is an observation from the Hubble telescope. It is a picture of a red galaxy, which is very, very massive and a long way away. And behind it is a blue galaxy, which you should not be able to see because it's behind a red galaxy, but you can see it, and it's gravitational lensing. So the blue light is bent around, a bit like the cloak I'm going to talk about, bent around this structure so that you can in fact see it as a ring. And there are many, many examples now of gravitational lensing. So that's another instance that space can bend light. Now, the other thing which you need to know, and why this is relevant, is that the distortion of space is described by something called a metric. And all it does is to show you just how much space is squashed or stretched in this direction and that direction, the other direction. And as far as light is concerned, the metric is very like the refractive index. So if you distort space, it's like making a lens for light. So, this is what a lens would do, okay? Send light to your eye by refracting it. And so curved gravity behaves like a lens. Well, here's a bit of formal theory. Ignore the equations for the moment. So here's a piece of space. It's made of rubber. Now, our insight, which we humbly added to Einstein's theory, our insight was that if you take a field line in space and then you bend the space, the field line behaves as though it's embedded in the rubber. So as you stretch the rubber, the field lines move with it. Okay. So our design procedure is to start with a flat space, and you have some field lines. Maybe there's a charge here or a solenoid or something. You have a magnetic or electric field line. They both respond the same way. And then if you want to rearrange where these field lines go, you don't push the field lines themselves, you stretch the rubber and watch where the field lines go. And when the field lines are going in the right place, you stop stretching. And then you say, thank goodness I don't have to do it because Einstein has done it. Here's a formula which in terms of derivatives and whatever, so this is the coordinate transformation taking x to x prime, oh, I've got UV here, sorry. And if you know the coordinate transformation, then this formula will tell you what values of epsilon mu will send the light in this direction. So we're pretty excited about that. We thought it was a rather powerful design technique, and something I've come to regret over the years is that we thought we'd demonstrate this by showing how we could design a cloak, and unfortunately it's a bit like the Sorcerer's Apprentice. This has taken off with a life of its own. Anyway, for what it's worth, here's how we did the cloak. This is Peter Pan. I don't know, anybody know the story of Peter Pan? Put your hands up. Peter Pan? Yeah, quite a lot of people. Not as famous as Harry Potter. Even more people know Harry Potter. But this is Peter Pan is the guy who lost his shadow. And what J.M. Barrie, who wrote the story, didn't realize was that if you lose your shadow, you're invisible. Okay? Because it's not enough to make something black, because it still has a shadow. And what you have to do to make sure that you're not aware that something's there is to get rid of the shadow. So when you've done that, Peter has lost his shadow and he's invisible. Now, how do you do that? Okay, so you're sitting there, the professor, you say, hey guys, to your PhD students, we've got to design this cloak, okay? And what it's got to do is to take the light which enters the cloak. It's not got to touch this hidden object in the middle, that's the object you're hiding, and you've got to guide the light around it, and you mustn't throw it away because there'll be a shadow if you do, and then it's got to come out the other side, going in exactly the same direction, as though nothing was there. Okay, simples, but you've also got to do it for light that comes in here, whether it comes in this way, that way, or the other way. It's a nightmare of a PhD project, right? Okay, you spend many computer hours trying to solve that in that way, but there's another way. So here's a piece of space, it's flat, and it's made of rubber. So I'm going to put my finger in the middle of that thing, and I'm going to tear a hole in it. And I'm going to push all the space out of that central region. And in this central region, I can put anything. I'm going to hide something in there. And remember that if I push the field lines, any light that's coming through that structure moves with the rubber. So you push all the, as well as pushing space out here, you push the light out here as well. Okay. But what you do not do is distort space in this region here. And if you don't distort space, the rays don't move. Okay. There are many coordinate transformations you can use to achieve this. Here's one, pretty simple if you like algebra. Plug that into Einstein, there's a formula for the cloak. Okay, go on holiday, come back, write your Ph.D. Now, I told that story at a DARPA meeting in San Antonio. David wasn't there, actually. His henchmen were there. And they reported back to David that there's this John Pendry at it again. He's got another idea. Can we do something? And very, very short order, God, these guys work fast. In a few months, David and his team, David is now at Duke University, built this cloak according to the design specifications. And you can see it comprises metamaterials. You can just see it's working at the RF, and it's in a planar cavity, so it's two-dimensional. And you can see that the metamaterial elements are graded from the outside to the inside, so that changed the refractive index. Not negative refractive index here, it's positive refractive index, but we are exploiting the ability of metamaterials to make a material that's not homogeneous. You can't make a cloak with a homogeneous material, but which changes the refractive index as you move in. And we've seen many examples of the cloak since those days. Now, back to Veselago. Veselago already realized that if you have negative refraction, then because you're bending the light back on itself, it will come to a focus inside this negative refracting material. What's more, you'll get a second focus outside. And Veselago knew that. But now, with conventional lenses, there's a pretty ironclad law due to a guy called Abe, which says that you can't see anything using a conventional lens, which is much smaller than the wavelength of light. And that is really a tragedy in biology, because the wavelength of light is about half a micron. And that's just about the size of cells. When cells get to be interesting, you can't see inside them with a conventional microscope. There are all sorts of tricks you can play these days, some of which have won Nobel Prizes, which enable you to do better resolution, but not with a lens. You do it in other ways. So that seemed a pretty ironclad law, and people thought that the Veselago lens was subject to this law. And when I was thinking about the Veselago lens, I was head of department, and my week was full of administrative things, and I did my science at the weekends. It happened to be Sunday. And I saw something very unusual about this lens. It was, if you got the parameters right, it had an unusual degree of lack of aberration and so on and so forth. So I asked myself, just how far does this go? Expecting to find out that it obeyed Abe's law, but in a very interesting way. And do what I could not get it to obey Abe's law. Maxwell's equations said this lens is perfect, providing you make it perfectly, and that is a big proviso. And that frightened me, because Abe's law is so embedded in the optical community that if you go around waving a flag saying, I'm breaking Abe's law, you quickly get put in the category of nutcase. And I was afraid that somehow I'd missed something. So I talked to friends who I knew wouldn't let me down, and they didn't believe it, but I said, well, why is it wrong? And they said, we don't know, but it's wrong. So after about 3 months, we plucked up our courage and we published this stuff. And there's a way I can explain it to you using transformation optics. So you saw how I made the cloak by taking a piece of flat space and then making a hole in it and pressing it. Well, I'm going to do a similar thing, only a bit more drastic, with negative refraction. So here's a bit of flat space, okay? And the middle bit I'm going to make negative refracting, and I'm going to do it by, first of all, I'm going to squash it. You can see my squashing space. And if you squash space, big surprise, it gets more refracting. And you squash it infinitely, greatly, and it gets infinitely refracting. Now you know what happens to infinity. 1 upon x goes up to infinity, and then the other side it comes down to minus infinity. So let me make a bit of an effort, squash it a bit more, and we've gone through the singularity, and now we have a piece of negative space, okay, squash it a bit more, and there's your perfect lens. Positive, negative, positive. But isn't there something weird about this? You've got 3 manifolds of space. So let's suppose we have an object here. Light comes in, it passes the object once, it then goes back on itself, and it passes the object a second time. It goes on, comes to the edge of the negative bit, and goes back, retracing its steps, and it passes the object a third time. And it's not an image, it is the object, as far as Maxwell's equations are concerned. So using a piece of cardboard, I proved to you that the lens is perfect. And actually, it has this interesting consequence for space. And if you think of yourself as having 3 realizations, you sit in this space, right? Then you realize that if that's all you say, there are a whole series of paradoxes here. How can there be 3 of me? One's enough, right? And when you work through those paradoxes, you find that in order for negative refraction to exist and be true, there are certain laws of logic it must obey, and those are dictated to you by thought experiments like this, which say you can't break logic, and therefore negative refraction, for example, has to disperse with frequency. That's one of the laws you can deduce. So it turns out that actually to make the lens perfectly is very, very difficult, because at least it's been done at RF, but at visible wavelengths, it's very difficult, even with metamaterials, to find a material with a negative refractive index. And so in that paper where I suggested that the lens could be perfect, I had a suggestion for a compromise. And it's this, that the way we think of light, it's a dance, okay? It's a dance between an electric and a magnetic field. And the beat of the dance is the frequency of the light, but the step of the dance is the wavelength. And the 2 partners of the dance are the electric and the magnetic field. So if you have an atom which typically emits an electrical signal with an electrical transition, the light has to travel half a wavelength before it turns into a magnetic field. But what if you're interested in really small things and really small distances, which are much less than half a wavelength? Then there's no magnetic field. And if there's no magnetic field, you don't care about mu. It can be negative, positive, whatever, because there's no magnetic field. Okay, so if you make a really small lens, then all you need to do is to make epsilon negative, because that's the one that responds to the only field there, which is the electric field. Mu can do what it likes. And there is a material which does that, and it's called silver. Any metal will do, but silver's the best. So here's a lens made in Berkeley by Nick Fang, he was at MIT, but he's now in Hong Kong, actually, with Jiang Zhang, who was the head of group. And so what do we have here? We've got silver, which is going to be a lens. We've got a spacer, and we've got an object, and we've got some light. And everything is like nanometers, and we've got a light which is several hundred nanometers, so the requirement of my suggestion is met, that these are all subwavelength. Now, since it's a wavelength, you can't actually see it with a microscope, so you have to write it in a photoresist, develop photoresist, and then look at what you've got. And this shows a grating with a resolution which is a sixth of the wavelength. Okay, it's not super resolution, but it's a lot better than a microscope could do. And in fact, perhaps more impressive to the eye is looking at the word nano. So here's the word nano scribed in chromium, which is, okay, this is the nano here. And if you don't put any silver there, you get this kind of blurred image. Here's a scan across one of the letters, the wavelength, long, and then you put in some silver. It's like popping your specs on. You get much higher resolution. So that was confirmation that you could, in fact, make something that would beat Abbe's limit. There are a lot of rows along the way, but I won't bore you with the incivilities that intruded on our research. What can we do with metamaterials? A whole bunch of things. Here's a list. So I'm going to work through that list, and then I'll come to my conclusion quite soon. So here's a super resolution microscopy, bit of microscopy. It's actually performed at UCSD by Xiaowei Liu. And what he has here is, well, this is a point source, and it's a point spread function imaged in a conventional microscope. And you see the point spread function is big, and with his metamaterial technology, using a hyperbolic metamaterial, that just means part of it is negative and part of it is positive. Nevertheless, it does much better, you can see. Here's a biological specimen, conventional microscope, Xiaowei's microscope, another specimen, and you can see that it's really getting a lot better resolution through using this metamaterial technology. Something else you can do in the focusing regime is to make very, very thin lens. You know that a lens is typically like lenticular, shape, fat in the middle, thin at the end. But you don't have to do it like that. You can have what's called a GRIN lens, or graded refractive index lens. And in that case, the lens is the constant diameter, and you just change the refractive index of the material as you go towards the center. And that has the same effect as making it thicker. And you can do that with metamaterials. Here is an adaptation of instead of having a ring, you have a sort of angle device made of metal that is resonant. It has this resonant structure. You can see its angle is changed. This angle here, the orientation and so on, and that grades the refractive index of this particular lens. And the point about that, and this is work done in Harvard by the Capasso group, the point of that is these elements can respond very strongly and yet be very, very thin. So this is a lens to work in the infrared at 8 microns. And this is a very thin lens indeed, less than a micron thick. That's in the infrared. A more recent example is some flat objects a meta-object lens. This is for 3D imaging, and it's been launched by an outfit called MetaLens, and this is a beautifully colored picture coming out of this silicon foundry. So what else? Oh yes, you can design metamaterials. Here's a metamaterial. You can't see the structure here because it's subwavelength, but this is a structure designed by Xiaobo Yin, who wanted to make a material that could cool buildings passively. So you know that on a hot summer's day in California, you need air conditioning, and you also know that air conditioning takes a lot of energy. And if you could somehow get a material that would give some cooling without expending any energy, that might help with global warming. And that was his objective. And he exploited the fact that the sunlight comes mainly with visible light. And that's where most of the energy is. There's some in the infrared, but most of it's in the visible region. Whereas heat, when it is in the form of radiation, comes at a much longer wavelength. And because metamaterials can have their properties strongly dependent on the wavelength of light, you can have materials which reflect sunlight. You can see this thing is shiny, and radiate infrared, far infrared light as heat. And in fact, in the daytime, at noontime, you can have a radiative cooling of 93 watts per square meter in direct sunshine. And I believe, I may be wrong here, but I did hear that this stuff has been installed in an airport in Singapore. So that's one thing. This is something called a phased array. Now, if you're communicating with a satellite, you really need to have something which points at the satellite. Typically, it's a steerable dish, about yay diameter, big dinner plate. And it's heavy, it's expensive, it consumes power. There's a neater way of doing it, which is to have a big block of silicon with lots of transistors in it and things, and it can appear to point at this different parts of the sky without anything actually moving physically. Now, one of the things about metamaterials is that they're very easily tunable, and you can change the tuning in real time. And so you can take a metamaterial, and through very, very simple electronics, you can make an aerial which points at different parts of the sky according to the electrical signals you send to it. Very like the array of transistors, only much simpler and much cheaper. And this company, Echodyne, who's made the PICs and so on, has installed this in this utility task vehicle, Nikola Reckless, prototype drone vehicle uses metamaterial. So that's another application in these phased arrays. Magnetic resonance imaging. Now, the signal from in magnetic resonance imaging is a magnetic signal, and it's very, very weak. And what's more, it's surrounded by your body, which is very noisy, okay, and electrically speaking. The reason magnetic resonance imaging works is that all the noise in your body is electrical. There's almost no magnetic noise. And therefore, if you have a magnetic signal, that stands out magnetically. But you've got to be very, very careful that you only collect the magnetic signal and none of the electrical signal. So it's a big challenge in pickup coil design. If that pickup coil picks up any of the electrical noise, you're dead in the water. You can't hear the magnetic signal. And Richard Sims, my college, he has designed, so typically a pickup coil would pick up the magnetic signal and then it immediately turn it into electric signal. Sheer madness, you know, you're taking this lovely, clear, pure signal, and then you're turning it into something which has to compete with this noisy environment. So you've got to be very careful how you bring it out of the machine. But Richard has a way of making a magnetic wire which brings the pure magnetic signal out. And if you've ever been in an MRI machine, it doesn't hurt, but it's a very, very noisy environment, and you stay in there for 10, 15 minutes and clatter, clatter, clatter as the magnets go bang, bang. You'd rather it be less than 10 minutes. I did mention right at the beginning that these ideas apply not just to electromagnetism. Function through structure applies to many sorts of waves. I'll just talk about one of them here. This is an acoustic situation. Ping Sheng, who was in Hong Kong until recently, is now in Cambridge, UK. He had a way of using metamaterials to screen sound. Now, particularly in Hong Kong, you can imagine if you're in a small apartment with a thin wall, the neighbor plays bass guitar, you're going to be in bad shape, sleep-wise. And in the building trade, there's a law which says that the lower the frequency of the sound you're trying to screen, the thicker the wall has to be, the more massive it is. Ping managed to break that law, and the way he did it was through metamaterials. So his basic unit is, guess what? A resonator. And his resonator is 2 centimeters in diameter. It's a membrane, an elastic membrane, and there's a little weight in the middle. Not surprised, you twing it and it vibrates. It's a resonator. And you put them all together and they talk to one another, and they can be persuaded to do all sorts of different things, including they've been developed by this company in Sonoblind, Metasonics, and their idea was to use a whole array of these resonators, and it's very light. Actually, it's like a massive wall. It's so light that you can make it into a big screen in a hospital, which you can wheel around. So maybe you have a sick patient, they're very ill, noise doesn't improve their conditions. You simply wheel these acoustic screens around their bed, and it cuts out all the racket from the surrounding parts of the hospital. And finally, mechanical metamaterials. You can design these things with very unusual properties. So here's somebody will have to explain it exactly how it works, but it's like this. If you take a normal material, like a sponge, and you squeeze it, the sponge will extend in the other direction, so you push it in and it goes out in the other direction. But there are other materials, that's called Poisson's ratio, and there are other materials with a negative Poisson's ratio, and you can design them using metamaterials so that when you squeeze that structure, instead of going out, it goes in. Actually, there is a natural example of that, and somebody pointed out to me the other day. It's a wine cork. Have you ever thought how you get a cork into a bottle? Because if when you squeeze the wine cork to get it into the bottle, it got fatter, it wouldn't go in. So a wine cork has a negative Poisson's ratio. Okay, it's not a metamaterial, but it's very helpful to those who like wine. And if you squeeze it, it actually goes in and you can get it in the bottle. Anyway. Okay, so very briefly, because I'm a minute over time, apologies. what for the future? Well, we've spent a lot of time looking at static structures, which, okay, they can be changed, but slowly. But what if you could make a material whose properties you changed on a timescale which was comparable with a beat of light? Then you have a whole range of things you can look. So because it's time dependent, you don't conserve energy. You can amplify light. Of course, the thing's throbbing in time, so it's not time symmetric. You break time reversal symmetry, and that's of interest to a lot of people for protected states and so on. You can compress radiation. And something else that can happen is you can generate singularities. And these singularities, I mentioned Einstein already, but one of the things that come out of Einstein's equation are the black holes. And black holes have this funny Schwarzschild radius, they call it. And Stephen Hawking, you've heard of Stephen Hawking, what he's famous for is that he was the first person to realize that there's a connection between the very, very big, the general relativity theory, and the quantum theory, which is usually thought of the theory of the very, very small. But what Hawking showed was that this singularity in the black hole actually emits radiation. So it's not only a black hole, it's a black body with a finite temperature, which Hawking predicted. Unfortunately for Hawking, and it's why he didn't get a Nobel Prize, because your theory has to be verified experimentally, nobody will ever see Hawking radiation because it's created inside a massive black hole. And in order to escape, although the radiation might be quite intense near the singularity, it has to climb out of this massive gravitational field, and by the time it gets out, it's so exhausted that it's got hardly energy at all, and you're not going to see it from Earth for sure. And the only chance we have is of building laboratory analogues of Hawking radiation. And there's a guy called Bill Unruh who specializes in this, and he has a number of systems which could potentially show Hawking-like radiation. And this adds another possibility to it, that when experiments catch up with theory and we make things move this fast, there's going to be emission of photon pairs from our singularity in these structures, and that will be a Hawking analog. So watch this space. And so to my summary, I'll finish there because you're all capable of reading if you wish to see my summary, because I'm over time already. Thank you very much for your attention.
Hi, my name is Jesus from Mar Vista High School. And earlier in your presentation, you mentioned how metamaterials can be used to cool down buildings and like combat climate change. I was wondering if you could see in the possible future if they can be implemented into our Earth's oceans to combat, well, climate change and coral bleaching in a way.
Mm-hmm. Mm-hmm. That's possible. I think in the case of the ocean, you might need quite a bit of metamaterial, and they're cheap, but they're not that cheap. Okay, so you would put them on a building, which is a finite structure, not as big as the ocean, and I think that's where they're going to be applied, actually, for the foreseeable future. There are things you can do in the ocean. The ocean is full of waves, and metamaterials about changing what waves do, where they go, whether they do any damage, and so on. So, the metamaterials have been proposed for interacting with ocean waves. So, yes, relevant to ocean physics. Thank you.
Concerning the applications for metamaterials, could they potentially alter gravitational waves in an unexpected way?
Oh. Metamaterials for gravitational waves, is that a...
Oh, wow. I wish. You know, it would be so much fun. There is one thing that gravitational waves do. I briefly mentioned that if you make a metamaterial that changes in time, so you can think of it, maybe you think of a metamaterial modulated in space, and then you make that modulation move, okay? A bit like a wave on an ocean. So the height of the ocean alters. You don't move any water, but the shape. So imagine modulating the refractive index like that. And that actually happens in a gravitational wave. So a gravitational wave alters the refractive index, alters not the refractive index, but the impedance of space as it goes through. So in our lab in London, we have some people working on what happens when a gravitational wave moves through a static magnetic field. And what happens is that it grabs some of the magnetism, and so as well as the gravitational wave, you have a little bit of light going along. So it's a possibility, because you can see light easily, and you can't see gravitational waves very easily. It's a possibility that you might be able to observe gravitational waves because they might have been through the intense magnetic field in a star, picked up some light, and carried it with them. And then you might see a flash when the gravitational wave. That's a speculation. I don't know if that can happen yet, but that's the sort of thing you can imagine when you start thinking about materials or even space, which is modulated in time as well as space. So thank you for the question. Very interesting.
My name is Lisa. I'm from Sweetwater High School, and I was just wondering, what skills or habits helped you succeed in your career, your research career, and how could high school students learn and develop those skills?
I'll need that translated.
So, what skills could you offer a high school student to perhaps succeed in the same way you have in your career?
Not to proceed in the same way. No, everybody's different, okay, but there are some basics. And as a student, you first of all, you need to acquire skills. That's what a student, being a student is about. You have to learn your math, you have to learn your physics, chemistry, and so on. So you have to have a skills base that you bring to any situation that you're going to encounter when you cease to be a student. And along with that goes other skills, which are social skills. So most jobs in this world involve interaction with other people in some way. So you need to develop your interpersonal skills. And in particular, when you go out into the world, I mean, maybe if you come from a family that's very rich and well connected, they will help you and so on. Most of us are not like that. And in that case, it's very helpful if you can find a senior figure who will be your mentor, somebody you trust, somebody you can go to and say, I want to advance to the next stage of my career. What steps should I take? That sort of thing. So find a mentor, somebody who's nice and kind and not necessarily clever, but source of good advice. Okay, thank you.
So maybe we'll take a question from this side first, so please go ahead.
Hello, my name is Sebastian Valdez. I am from CETIS Tijuana, and thank you again for the outstanding lecture. My question is, do you think there will be future applications for metamaterials in the area of astrophysics or observational astronomy?
Well, there is this Hawking thing I talked about that awaits experiments which can move on that sort of time scale. Metamaterials are about controlling radiation, And our primary means of observing the universe, until gravitational waves came along, is electromagnetic waves, whether it be light or whether it be radio signals. So you can imagine metamaterials having quite a role in helping a radio telescope see better and further. So yes, it's rapidly becoming just another technology to which you can turn when you want to do things better than you're doing them already. Mm-hmm.
My name is Shrina. I attend Del Norte High School here in San Diego. So Dr. Pendry, you spend a lot of time throughout your life in academia. How would you say that your experience learning and exploring science has changed between your university and high school days versus now through your work as a research scientist and a professor?
Yeah, so you spent a lot of time in academia doing research. The question was, how do you think of things differently between perhaps you're studying science from your high school days on through your career up until now?
It's a question of independence. So when you're a high school student, unless it's a very unusual high school, you're a sponge. You're soaking up information. And basically, when I was a high school student, I knew so little that I didn't have so many thoughts on my own that were significant, and that's the difference. That you become much more independent in your learning process. First of all, when you go from high school to be an undergraduate, you have to take more control of your learning. You have to make decisions about which things you concentrate your attention on according to where you want to take your career. And then again, when you're a Ph.D. student, or if you go out into industry and work there, the independence gets greater, and you start having to initiate your own projects. When you're a scientist, only part of what you do is actually being very clever at doing math or experiments or whatever. The real skill of a scientist is to pick the right problem. So get smart at picking the right problem. Pick the easy ones. That's a piece of advice, I suppose. Okay, thank you.
Okay, I've been told that we have to wrap up this portion. What I'd like to do now is just, we should all give Sir John Pendry a round of thanks for giving us the invitation. Thank you.